Okay, good morning everyone. I decided to take the tutorial this week because of our semester test coming up on Saturday. If someone can confirm that they can hear me, then we can continue. Can anyone hear me? Okay, Ms. Opperman says that she can hear me, so we'll continue. Okay, so your test on Saturday will be only written, so there won't be a multiple choice component. The test will be either out of 25 marks or 30 marks. I'm trying to get together some more questions to make it a 30-mark test. And I'm still trying to decide how long it needs to be. Now, the important thing for me and for you in this session is that you have an idea of what I expect from you. And the reason I'm doing this is because I've had a look at what people have sent me. So just to be clear, not many people, not many students have sent me attempts of the tutorial work to look at. I think I've only had attempts from about 5 or 6 different people. And most of those were terrible. You need to understand that the way you need to write things out is different from intuitively understanding what's happening. So when you tackle a problem, you might see or you might suspect that a particular series is divergent. But when you write out the solution, you need to be able to justify all the steps in your reasoning with only the theorems that we did. And that's very, very important. I'm not going to you can't get marks for things that are in your head or vague arguments. So in order for me to illustrate what I mean, I've prepared a few things which I want to show to you. Unfortunately, I didn't get enough time to prepare as much as I want to, but I think what I'm going to show you will illustrate what I'm trying to say. Okay, so I'm going to share. Okay, so here's what I want to do in this session. I want to spend the next 10 or 15 minutes talking about this stuff because it's very, very important. I'm recording the session, so if at any point between now and Saturday you want to review what I've said, then please do so. If you've got friends in the module who are not attending this session, please tell them that the recording is there and that they need to go and watch it to make sure that what they give me on Saturday is what I expect. Otherwise, you're going to get terrible marks. Okay, so let's start. Let's spend the next 10, 15 minutes doing that. And once we're done with that, then we can switch over and do what we normally do. You raise a problem, we talk about it, I try and write it out for you with one exception. Unfortunately for today, I've forgotten the tablet that I use for writing on. I'm still going to write. It's probably not going to be as clear as it would have been. Okay, so we'll see what we can do. For me, the first part is the most important. Okay, I'm going to share my screen. And let's start that again. I'm going to share my screen and then take you through what I'd like to explain to you. And then afterwards, we'll see how we tackle problems together. Now, if you've had a look at the lecture notes for this week, which I'm not sure if I've loaded yet, but I have loaded the videos. So the section for this week is on a strategy for testing series. So what they've done in the textbook is they give you hints for how to approach a particular problem based on the form of the problem. So what I've gone and done is I've expanded a bit on the hints that they've given you for each of the examples, put in the details of the steps, and shown you how many marks a particular problem would be worth. So look at example 1. Let's start there. Example 1 says, essentially it would say, determine whether the following series is convergent or divergent, right? And the solution in your textbook says simply, this is 11.7 now. So if you've got your textbook in front of you, you can page there and see that example 1 of 11.7 simply says, since AN converges to a half, which is not 0 as n goes to infinity, we should use the test for divergence. So I've added some details that show you how I want you to write out the solution, how I need you to be able to write it out for you to get all the marks. So first you would do the following. You would calculate the limit. The limit as n goes to infinity of n minus 1 divided by 2n plus 1 is equal to the limit as n goes to infinity of 1 minus 1 divided by n divided by 2 plus 1 over n. Now, there we've used a strategy which has come up a few times. It comes from 1a when we calculate limits that go for the variable going to infinity, and we get an answer of a half. Now your reason goes as follows. Since the limit, remember an arrow half is the same as saying the limit of an as n goes to infinity is a half, which is not equal to 0. We know from the test for divergence that the series, the sum from 1 to infinity of n minus 1 divided by 2n plus 1 cannot converge. Now, notice what I've done. I've looked at the example and thought, okay, this probably diverges. And the reason, the theory that I can use to back my claim that it diverges is the test for divergence. Now, if you look at page 713 of your textbook, at the bottom of the page, you'll see the test for divergence written out in detail. It says, I'm reading it to you, if the limit as n goes to infinity of an does not exist, or if the limit as n goes to infinity of an is not equal to 0, then the series, the sum an, is divergent. Now, notice what I've done. Each of these tests, each theorem, each result that we use has a set of conditions that need to be satisfied and a conclusion that can be drawn. In the case of the test of divergence, the conditions that the sequence must satisfy is that either the limit doesn't exist or the limit, if it does exist, is not equal to 0. Those are the conditions. It must satisfy one of these two. The conclusion I can draw is that the series is divergent. And so I need to, whenever I use a theorem that we've discussed in the module, I need to show that for a particular exercise or problem or example, that the conditions for that theorem are satisfied. And we'll see this again. I'm going to show you 3 of these examples, right? And I'm going to show you in each case how I explain that the conditions are satisfied. So there, that tick mark, the first bit where we say we calculate the limit, and then limit n goes to infinity, yada, 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 that's showing that the limit is a half. Then in the next line I say, since the limit is a half, which is not equal to 0, we know from the test. In other words, what I'm saying is, I've shown now that the conditions for the test for divergence have been satisfied, and hence I can draw the conclusion, which is that the series diverges. If you don't write it out like this, I'm not going to give you the marks. And, you know, I think I don't actually need to show you this, because all of the examples are done with the requisite amount of detail. So if you follow what the examples do, then you'll do the right thing. Let's look at another example. Okay, I didn't do example 2 or 3. I did do the details for example 4. Okay, keep the questions coming. We'll look at them in a minute. Okay, so send the questions. I will look at example 4 and example 6, and then we'll stop, and then we'll look at some more examples of things that students have sent me that I've corrected. I'm not going to tell you who the students are, but I want to show you what my comments to them were. Okay, so example 4. There we've got a sequence, we've got a series, the sum from 1 to infinity of -1 to the n times n cubed divided by n to the 4 plus 1. And so the example simply says, the example in the textbook for this section simply says, since the series is alternating, we use the alternating series test. Now remember what the purpose of this section is. It's simply for us to have a strategy to figure out which of these tests to use for a particular problem. And so that's all the textbook says in example 4. And here's what I would want you to be able to write. First, I say what Bn is. Now, in order for you to follow my explanation here, I would say go to 11.5 in the text page there in the meantime, and go to page 732. Right? So now, notice what the conditions are for the alternating series test. We've got to define what the Bn is for this particular problem. And we have to show that the Bn is a decreasing sequence. Then we have to show that the limit of the Bn is 0, right, as n goes to infinity. Then we can draw the conclusion. So here we go. We say, I'm saying now, let Bn be equal to n cubed divided by n to the 4 plus 1. Now, the sequence Bn then is a decreasing sequence. How do I know that? Well, if I had to do this problem, I would show it by defining f of x to be the function which is defined for all real values. The function f of x is equal to x cubed divided by x to the 4 plus 1. Then I would take the derivative and show that this function is decreasing after some point on its domain, right? After some part, it doesn't have to be from 1 to infinity. In the ideal situation, it's from 1 to plus infinity, but it doesn't have to be. It can start at some point further after 1, right? And so I've done the one condition now, that the sequence is decreasing. Then the limit is n goes to infinity of n cubed divided by n to the 4 plus 1 is 0. You've seen how to do that in the previous example. Show it, show the detail. Hence the series we started with is an alternating series. Right? That's what it means for it to be an alternating series. hence it converges. Actually, no, it's not. For it to be an alternating series, all we need to know is that the signs alternate, right? So, but we've got an alternating series that satisfies the conditions of the alternating series test. That's the important thing. Hence, it must converge. And there you can see I've got 6 half ticks, which gives you 3 marks. Right? I might actually increase if I expected you to write out the details for f of x equals x cubed divided by x to the 4 plus 1. Its derivative and showing that it's decreasing, I might add another full mark to that, making this problem 4 marks. But keep in mind, to get the 4 marks, you have to do all of that work. Right? Next one, we'll do one more, then I'll look at the comments and questions coming in. Okay. Example 6. Look at this one. It says, again, determine whether the series is convergent or divergent. So, remember in one of the lectures I gave you the rules for inequalities that come from the Appendix A in your textbook. Now, those rules are very important because a lot of this kind of mathematics is based on inequalities. Okay? Analysis is based on inequalities. This module is a module in analysis. Okay? And so we need to use those rules for inequalities to justify our reasons, to justify our reasoning. In other words, they become the reasons why things are the way they are. And to start this one, I would say, for every natural number n, using rule 1 of the rules for inequalities. Now, you can go and look up what it is. I want you to write that in your test on Saturday. I want you to know where it comes from. Right? Using rule 1, we can say 2 plus 3 to the n is greater than or equal to 3 to the n. Right? Next, I'm going to take the reciprocal of these numbers. And because of rule 5, I know that if I take the reciprocal, then the direction of that inequality swaps. In other words, 1 divided by 2 plus 3 to the n is less than or equal to 1 divided by 3 to the n. The reason is rule 5. Next, consider this series now. The sum of 1 divided by 3 to the n. Now, this last series is a geometric series with the absolute value of r equal to 1/3, which is less than 1. And since it is less than 1, that absolute value of r, we know that it's a convergent geometric series. And by part 1 of the comparison test, we know that the sum from 1 to infinity of 1 divided by 2 plus 3 to the n must converge as well. Again, I've shown you here the things that I will look for to give you the marks. So on Saturday, you can't tell me you don't know what it is I'm looking for. Okay, I'm going to stop sharing for a minute, for a bit, and then we look at the comments coming in, and and then after that we can move on. Okay, let's look at the comments. Okay. Okay. Mr. Wu says, so will we get the full mark if we write down like example 1? Yes, if you write it down like I've done example 1, you'll get full marks. Mr. Naika says, can we say that the function f of x is decreasing because the denominator increases quicker than the numerator? Can we say that the function f of x is decreasing because the denominator increases quicker than the numerator? You can say that, provided that you can write it as an inequality. So that's a very good idea, Mr. Naika, but it's a very good idea, no buts. I want you to see how you would write what you've said there, that the one function, remember you've got two functions now, you've got a fraction. So you've got a rational function. Show to me, in terms of inequalities, that the numerator is increasing slower than the denominator. In other words, do what you've done using inequalities. I hope that answers your question. PTM Malobola, for example 5, if you just state that the denominator increases as n goes to infinity, hence function decreases as the condition rather than, is this still correct? If you just state example 5, I have to look at it quickly. Example 5 or example 6? I think you, no, I don't understand example. We didn't do an example 5. Okay, Mr. or Miss Malobola, please figure out what it is you're talking about. We didn't do example exercise 5. Next one. So we have to write detailed conclusion after every calculation plus the test we use to reach conclusion 100% in Salakupatwa. Yes, in Salakupatwa. 100% correct. Are the rules for inequalities the ones on page A4 of appendix? Yes, Ms. Opperman, they are. Plus, in your notes, if you've been reading your notes regularly, you'll see that I copied them there for you. So I spent 20 minutes retyping them from the textbook so that you've got them in your typed notes. I think look at the notes for week 3. They should be there. BK Derwai. Can we solve example 6 by suggesting 1 divided by 3 to the n as a p-series? Example 6, let's have a look. Example 6 as a p-series. As a p-series, does that make sense? Isn't a p-series, a p-series is the variable is in the base, right? Let's look at your question again. Can we solve example 6 by suggesting 1 over 3 to the n is a p-series? Actually, I think no, because remember the p-series looks like this. It looks like 1 over n to the p. The geometric series is 1 over a number to the n. So the difference between geometric and p-series, BK Derwai, is the fact that in the p-series, the variable is the base. In the geometric series, the variable is a constant. So in example 6, 1 over 3 raised to the n is a geometric series where the common ratio is a third, 1 over 3. Okay? I hope that's fine. Check me, let me know if you're happy. Next one. If we apply theorems, how do we write that down? Do we write the theorem in full? No, you don't have to write the theorem in full. We know the names of the theorems. Say, the test for divergence. It's got a name. You don't have to write the whole test. But you have to show me that the conditions for that test are satisfied. O.L. Mohuame. Are you happy? Or we can say, for example, by squeeze theorem, then finish off. Yes, exactly. Okay. I think we've solved this questions. There's one from Malobola. You still need to figure out what it is that you're referring to. Let me know. Okay. We've scheduled this session to go until 10:40. So let me continue because I want to show you some more examples. I don't want anyone in this session afterwards to say they didn't know what was expected. Okay? I didn't see the lectures slice in the week 6. Can you upload it? Yes. I haven't loaded the notes, but I haven't loaded the notes. I'll load them. They're ready. I've just forgotten. But the recording is there. Okay, so there's a recording. Also notice I'm loading the recordings different now. I'm loading the recordings in such a way that you can actually play it inside Blackboard, right? And I know that I still owe you tutorial problems for this week. I'm running a little bit, I'm chasing my tail a little bit this week because I've got so much to do. And that's why I haven't posted new tutorial problems, but they will come today. I thought it was more important that we have this conversation about the Saturday test. Okay, now let me find the next thing I want to show you. And then we talk through another solution in detail of something. And then we can stop and look at some of your problems. I must just find this quickly. So if you've got more questions, keep them coming. Okay, I'm going to show you okay, let's have a look. I'm going to share the next one. I'm going to share the next PDF. Okay. Okay, so you should be able to see a solution now. Okay, so there's something similar to what we looked at now. The sum n from 1 to infinity of n cubed divided by n to the 4 plus 4. Now, look at 1 divided by, look at that first line that I've marked with a star. The sum from 1 to infinity of n cubed divided by n to the 4 plus 4. Or n to the, yes, it's n to the 4 plus 4. Now, the writing's a little bit faint, but there's an equal sign, and there's an equal sign. And so that first line, the mistake there is, there I've written it. So here in red you can see it easier. Here above you are saying the following. N cubed divided by n to the 4 plus 4 is n cubed divided by 4 plus n cubed divided by n cubed divided by n to the 4 plus n cubed divided by 4. But that's not true. The other way is what you're confusing it with. So when you turn it, when you make the denominator the numerator and vice versa, then you can do that, what you're trying to do. But the problem is, this is true, but it's useless for us. It can't help us to solve the problem. Right. Look at the next one. Now we want to show, we know that we want to use the limit, not the limit, the integral test. And so we take the integral of this function. But what's the problem with that? Well, if you think about it, the problem is if we've got a sequence, then that sequence is defined only for natural numbers. So it's not a continuous function. Remember in 1a, we spent a lot of time talking about continuous functions before we spoke about integrating them. Because if a function is not continuous, we can't integrate it, right? We can only integrate subsections of the functions over intervals over which that function is continuous. And so the way to do this is to start like this. You need to redefine a new function, f of x cubed divided by x to the 4 plus 4, then show that that's decreasing by taking its derivative, right? Right. Okay, I'm going to stop sharing, have a look at comments, and then we look at one more and move on. Okay, Mr. Naika says, for example, 6. When you said rule 1 and rule 5, do we actually have to write the rule down? Mr. Naika, if you said rule 1, it should be a... Yeah, actually, you raise a very interesting point. I would prefer that you write down the rule. So I would prefer that in a little block in the top corner of your script, you'd say rule 1 for the rules for inequalities. If A is less than B, then A plus C is less than B plus C, where A, B, and C are real numbers. And rule 5, if 0 is less than A is less than B, then 1 over B is less than 1 over A. It's better if you write it out in detail. I agree. Okay, I'm going to share again one more time, and then we can stop, right? Then we can stop. We'll look at one more attempt. I'm going to share again. Okay, let's look at this one, right? I'm going to show you the comments that I wrote for this student. By the way, thank you very much for the students who sent things. It gives us something to work with. I hope you don't mind me showing what you've sent. It's completely anonymous. I'm not telling anyone whose work you are looking at. So look at this one, right? Let's see if we can make it full screen. Right, look at this one. Look at the first step there. So this question was question 40 in 11.2. It says, determine whether the sum from 1 to infinity of 3 divided by 5 to the n plus 2 divided by n is convergent or divergent, right? Now, look at what we do. The first step that we did here was to say the sum splits over the two components inside the bracket. Now, what's the problem with that? Well, the problem is the following. That is only allowed if we know that the component series, the ones in line 2, that those converge. If we don't know that they converge, then we're not allowed to take that step. So I've said you are using theorem 8 on page 714 here, but you cannot use it here because in order for you to know that that combination converges, you must first know that the component ones converge, right? Now look at the next step. Now the limit as n goes to infinity, 3 over 5 to the n, yada, 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 yada. We prove that it's equal to 0. That's fine, but it doesn't help us. Why are we doing that? The same thing with the section in the middle. So there's nothing here that is either correct or should get marks. So here in the corner at the bottom is the correct solution. We have to reason our way through it. When we look at the problem, we see, okay, the 3 divided by 5 to the n, that's a geometric series. The other one is a p series with p equal to 1. It's really 2 times the harmonic series. And so my suspicion is I'm adding a convergent to a divergent series. And I think that means intuitively I'm thinking it must mean that the whole thing diverges. Right. Now, but now I need to show it. I need to prove it logically. So here we go. We say, so I'm going to reason by contradiction. I'm going to say, okay, suppose that it does converge. Well, if it converges, then we can use it in the following way. We can say the sum of 3 divided by 5 to the n plus 2 divided by n can be split in that way. And so we know that the sum of 3 divided by 5 to the n converges. And now I can write the sum of 2 divided by n as the convergent sum that we started with minus the sum 3 divided by 5 to the n. And this 3 divided by 5 to the n we know is a convergent geometric series, and hence we are adding 2 convergent series. The whole thing must converge, but then that means that the sum of 2 to the n must also converge, right? And this contradicts the fact that we know that the sum of 2 to the n diverges. And that's the way to handle this problem. Because of the contradiction, we must know that it diverges. Okay, I'm going to stop sharing again. We'll spend a minute or two looking at the comments. And then we can take a break and start again. Please, can you show us how marks will be allocated for a question where we are asked? Okay, there's a couple of questions here. PTM Malovolo. So, like the P-series and geometric series could be used to conclude if a series converges, one can also use squeeze theorem. Squeeze theorem, I think, is mentioned in 11.1, right? I think the answer to that question is yes, Malobolo, because we actually do mention it in section 11.1. We do have the squeeze theorem mentioned there, and if you can find a way to use it, 100% you can use it. In fact, it is on page 698. But keep in mind where the P series, where the squeeze theorem is mentioned, where the P series is mentioned, it's mentioned for the convergence of a sequence, not a series. So that's different. So you look at your question, you say like the P series and geometric series could be used to conclude if a series converges, one can also use the squeeze theorem. Yes, we can. Okay? Yes, we can. But keep in mind that the way it is mentioned in the textbook is it's being applied to sequences. So you can still use it to show that a series converges, because to prove that a series converges, we need to show that its sequence of partial sums converges. Okay. Mr. Naika says, please can you show us how marks will be allocated for a question where we are asked. I'm going to make a note of this because I'll have to go and look at an example where we are asked if a sequence is monotonic or bounded. I'll make a note of this. And then we'll move on because I won't be able to get one immediately. Okay. Ms. Opperman, is the level of detail in the solutions posted for this tutorial sufficient? No, I want more. I want what I've shown you here. That's why I'm doing this session, right? And Klabati, so if we have sum of series and the other converges, therefore the other converges as well. What's the other and other? You need to be more specific. CK Wu, when will we start the semester test 1 and will we have past papers? Mr. Wu, I'm thinking 8 or 8:30. I'll post all the details, obviously, 8 or 8:30. Past papers, I'm not sure if they make any sense. I can try and find some for you, but I didn't lecture this module last year. So even if I load past papers, they may not be representative of what you should expect. If I find them, I'll load them, but to answer your other question, either 8 or 8:30 on Saturday morning you'll start, and I'm guessing it'll be an hour to an hour and a half. Okay, I need to double check what's the standard time. I think the standard is 2 minutes per mark or something like that. Once I've checked, I'll let you know. Okay, let's take a break. We'll start again at 10:50, and then we can look at problems that you've posted.